SwayamPrabha. Digital India. Educated India.
In the last lecture, what we did is that we said that how you can actually invoke some kind of an averaging technique, so that you do not have to explicitly track all these interfaces, rather take a very macroscopic view of a multi-phase systems, which may be enough to do some design, some analysis, build newer systems. So, it may not be always the same type of fidelity that may be needed. So, we introduced the Eulerian volume averaging technique, which if you recall was something like this, okay, where there is a volume element and then there are within that volume element there are sub volume elements like of each phase, okay, and we also said defined a few rules. We said the net volume is the sum total of the individual volumes, we defined something called a volume fraction, and then we also did something called this volume fraction, summation of this volume fraction has to be equal to 1, which is logical. So, the Eulerian volume averaging is expressed as this, where this is basically an averaging notation, okay. This is an averaging notation. So, this actually means an average, okay. So, this volume average means if you look at this expression, what we have done is that for each of the phases k1 to pi, we have taken that quantity whatever that property is phi k across those each elemental volumes that is occupied by those individual phases, right, and we have integrated it over that particular phase and then we have summed it across all the phases, that is what we have done, right, and then we have divided it by the volume, right. So, imagine a situation. So, these are, say, let us keep it simple. So, this is like phase 1, this is like phase 2 and this is the elemental volume V. So, what we have done is that we have taken the whatever property that is there within this control volume, within this elemental volume, there is property variation, we have averaged them over each of those elemental volumes, right. So, that the total gives you a total average, okay. So, this phi k x, y, z comma t dv integral over this delta v k basically means what? You are basically averaging out the quantities in each of those elemental phases, right. If over each of those elemental phases you are basically averaging them out, got it. So, that is the most important part of this. So, no information that how it varies in each of these elemental volumes is actually retained, right. You are basically averaging the whatever variation of phi that you have, you are averaging it out across that phase, right. Okay. So, it might vary in some way, but you are averaging that out, and not only that, now you are averaging it over all the phases also. This is for one phase, okay. So, now for this phase also you are doing the same. So, you add this plus this, okay, and you get this, okay, and then you are dividing this entire thing by that elemental volume. So, this will give you the phase averaging or the volume averaged quantity, okay. So, this phi that you see over here, it does not belong to any one phase, it is the sum total. So, if that is density, say for example, it is the density of phase 1 and the density of phase 2, and it gives you some kind of an average density of the system, right. So, if you do it something like this, say it is a water, liquid water, water vapor kind of a system, if you average the things out, right, it will give you an average quantity for the density, okay. So, if say we take this example a little forward, so let us say for example, there are only 2 bubbles in a predominantly liquid system, right. So, what we are exactly doing over here, over each of this volume we are averaging the density, say for example, and for the liquid we are averaging the density over this whole thing, right. Okay. So, what will happen you are basically doing this averaging of the vapor over that small volume V1, let us assume, okay. Then you are doing the same thing for this volume V2, which is this volume. These are all very small elemental volumes, say for example, right, okay. So, you add these two quantities together, okay, that is what you have done, okay, by averaging, and then for the larger volume where it is all liquid water, say for example, you do liquid water into some volume V3, right. So, in your essential thing comes out to be rho 1 V1 plus rho 2 V2, rather not rho 1, this is rho V plus, let me do this, let me show you this in a more logical way. So, it is rho V V1, there are only two bubbles, say rho V V2 plus rho L V3, right, and this is divided by V1 plus V2 plus V3. All these are elemental volumes, right. That is exactly what this expression means. Got it? Clear? Okay. So, if for example, in this particular case obviously the liquid density is a lot higher than the vapor density, right. So, you will get an average which is more closer to the liquid density, right, because liquid density is multiplied with a very large volume and the vapor density is multiplied by a very small volume. So, it is very natural that you are going to get a density, right, which will be more closer to the liquid density, correct. However, if I take the reverse scenario where there are, say for example, liquid droplets exactly like this in a predominantly vapor volume, these are liquid droplets. This is a reverse problem, right, instead of bubbles now you have droplets, okay. Now, the same thing, same methodology will be valid here. Now, instead of rho V, what I will do is that rho L into V1 plus rho L into V2, right, plus rho V into V3 divided by V1 plus V2 plus V3, right. Now, here of course, there is a little bit of an issue, that is because if since rho L is much greater than rho V, right. So, you cannot say that the density will be very close to the vapor phase, okay. But however, if the liquid droplets are very small, say for example very small, this is a very sparsely populated system. Remember that epsilon k that we defined. So, let us say for liquid water this is about say 0.001, right. So, it is 0.1%, okay, and for the rest it is like 0.999, right, for the vapor. Now, if that is the case, in that case you can safely say that this averaged rho, that means this rho average will come very close to the average of the vapor phase in that particular case, because it is very sparse, right. On the other hand, if say these droplets are very giant droplets, right, that means this epsilon L say becomes equal to say 0.3, okay, 30% of the volume of this vapor space, then this rho, okay, will approach closer to rho L because of the simple reason that rho L is much greater than rho V. Okay. So, understand the averaging procedure. Okay. It is dependent on volume obviously, that the extent, not just volume, it is basically the volume fraction it is dependent on. It is also dependent on the actual nature of this quantity. For example, if it is rho, how does rho change across the two phases? Okay. In some other kind of a substance, the density difference may not be this much. Now, this is not just for densities, valid for other types of things as well. So, the key feature for choosing this kind of an averaging is that the volume element must be large enough to yield a stationary average, that is the first thing, okay. And for any variable or property that is associated with a particular phase, okay, we can also do something which is called a phase averaging, okay. So, what is phase averaging? First, let us look at these two quantities here. One is called an intrinsic phase average. What does intrinsic phase average means? You are integrating the property over the elemental volume that is occupied by that particular phase only, right, and then you are dividing it by the total volume of that particular phase, got it. So, it is the average that you are getting, okay, for a particular property belonging to a particular phase over that phase only, it is not overall, it is over that phase only you are getting a variation, right. On the other hand, the extrinsic phase averaging, you are averaging a particular quantity, a particular property belonging to a particular phase, right, but you are averaging it over the, you are dividing it by the net volume. So, instead of the volume of that particular phase, you are averaging it over the total volume, but you are still doing the average, doing the integration over the phase volume only. Okay. So, that is the two difference, and these two are related just by applying the volume fraction, right. You can apply the volume fraction to this, you will find that this will boil down to that. Okay. So, extrinsic and intrinsic phase average are related to each other. Okay. So, you know the volume fraction, you can convert one from the other. Okay. They are also related now to the volume average. Volume average is this quantity, volume average is all phases combined, right. This is for a particular phase only, remember this is still valid for a particular phase. This is the property that is belonging to a particular phase. Okay. So, it is like the rho, if you from this density problem that we just showed, for example, in that case it is rho L, it is averaged over the liquid phase, that is intrinsic. When rho L is averaged over the entire thing, okay, but still it is rho L, right, that is actually called the extrinsic averaging, okay, whereas this volume average is nothing but this rho. Okay. So, that is the information, that is how we are actually defining it. Okay. So, the rho average or this average, the volume average is related to the individual averages. For example, the extrinsic averages, if you just sum the extrinsic averages over all the phases, you get the corresponding volume average. If you do the same for the intrinsic phase multiplied by this epsilon k, you recover the ultimate volume average. Okay. So, these are also related. So, phase average and volume averages are related, intrinsic and extrinsic phase averages are also related to each other, clear. Okay. Now, there are some deviations from a respective intrinsic phase average value. Say you take any quantity phi k, remember here phi k is a field quantity. So, that means it varies even within that elemental volume of that particular phase also it will vary, right. So, when you take this phi k averaged over the individual phase out, there will be some kind of a dispersion, right. It is like a fluctuation, it is like always happens. Say for example, there is air in this room, right, I take the average concentration of air, right. Okay. If you subtract that out from the individual from the local concentration of air, right, you will get a variation, right. So, this is exactly like a dispersion or deviation. Okay. So, this is like a first moment, you can consider this like a first moment, right. So, this is the intrinsic phase average, it has been taken out from the local fluctuation, but that means the actual quantity phi k that varies within that control volume or that elemental area space, got it. Okay. So, this is, so there are three key concepts that we have found. One is what is a volume average, what is an intrinsic phase average, what is an extrinsic phase average, how these intrinsic, extrinsic and the volume averages are related to each other, and lastly we have found out what is called the deviation from a respective intrinsic phase averaged value, got it. Okay. So, these are several important things that we learned in this particular slide. Okay. There are some 2 or 3 important rules that I am going to narrate over here, and so listen to them very carefully. This picture I am putting over here so that there is no confusion, you can still correlate. This was the same picture that we saw earlier. Now, here what you can see is that if this is a products of 2 variables are phase averaged. Okay. So, one variable say is mass, other variable may be say velocity, Okay. It can be any other combinations like that. When two quantities are basically phase averaged, this is intrinsic phase averaging, as you can see over there, right. Intrinsic phase averaging, it is given by the individual intrinsic phase averages, product of the individual intrinsic phase averages plus whatever is the dispersion or the deviation, average of that. Got it? It is very similar to those kind of methodologies, that if you take rho and V, say for example, if you average them, rho L, V L, if you average them, right, that is averaged over the, say, the liquid. Okay. This is what it is, this is rho L averaged over L, right, V L averaged over L, correct, plus rho L V L averaged over L, right. So, this is nothing but this rho V. Okay. It can be any other things, obviously, I am just giving you an example, this is written in that particular fashion. Okay. Similarly, this is intrinsic, this is extrinsic phase averaged, is nothing but you write basically the same thing, except there is an epsilon k now, okay, because epsilon k comes from the volume fraction, and here of course it is not averaged, it is not with respect to k anymore, right. This is the complete phase averaging with, this is the extrinsic part. Got it. So, this is the rule number 1 that we establish, got it, in the product of the two things. Rule number 2 is this particular thing, stuff that we have here, right. When you phase average, when you average basically, this is also extrinsic phase average, okay, of a partial derivative of a particular quantity belonging to a particular phase. This is given by the quantity itself, right. This is the phase averaged of the temporal derivative, right. So, that is equivalent to the variation or the temporal variation of the averaged quantity, got it. So, temporal of the averaged quantity minus this flux term, okay. This flux term, this I is basically the interface velocity. So, it is the interface velocity, and this A k is once again the area of that individual component of that individual phase, okay, and this is the total volume. This is the extrinsic phase average. So, the total volume comes into the picture, got it. So, this is the phase average, extrinsic phase average of the temporal variation of a quantity is nothing but the temporal variation of the phase averaged, extrinsic phase averaged quantity minus this additional term which is given by the interface, which is given by the. So, it is basically like an through the interface something is going out, this is like a flux term, it essentially looks like a flux term, right. So, that is what it is, okay. Similarly, okay, so that is rule number 1, okay. Similarly, the volume average of a gradient, so you have a gradient of a particular property, right, it can be anything once again, it is a grad of a particular property, it is basically the grad of the averaged property, right, plus once again you have this particular kind of a thing coming into the picture, okay. So, this is once again another additional term that you incur. Similarly, the volume average of a divergence of a quantity, this is divergence operator, right, that is given as the divergence of the volume averaged of the phase average, extrinsic phase averaged quantity plus once again the same term, got it. So, 3 rules, this and this, all of this you can actually work out and why they are so, got it, okay. So, once we establish these rules, things becomes a little bit more simple, right. So, these are the rules which will come in very handy. So, just to do a recap, we did define how the averaging should actually work, and then we defined that how we can actually average when there is a product of 2 variables, and then we established certain ground rules that when you actually have a temporal derivative, if we have a grad and if we have a divergence, how to deal with them, right, because these will all be needed when you actually do the momentum balance and other things, right. Okay. So, this basically ends this particular thing. So, the rest have to we have to go start looking at that when we now actually do such a thing, how we actually can get into the we can write the generalized equation now. How we can write the generalized equation like the volume averaged multifluid models, if we talk about that, how we can use these rules basically to formulate those equations. So, let us go to the Windows journal and show volume averaged. So, if we look at now volume averaged multifluid models, this is the important thing that we are going to do over here, with all the experience that we had gathered. So, for the continuity equation, and we will just introduce it and then we will take it up in the next lecture. So, there are so the volume average multifluid equation means you are doing the volume averaging for each of the phases and each of the fluid components, basically the phases over here. So, the continuity equation is the volume average for the kth phase by taking extrinsic phase averaging. So, basically this equation you already knew, right, from the differential formulation without any assumption of incompressibility, that is what you have, right. Now, if you take the first term, you already know what it is going to be. It is going to give you right minus 1 over the volume A k rho k V I, V I is the interface, N k d A k, right, that is the first term. Similarly, the second term over here, so this was the first term led to this, the second term plus this is the rules that we established, right, using the same, so rho k V k dot N k d A k. Got it? So, basically nothing but we have applied the rules. So, using these two, we can write if this equation is say 1, so equation 1 now becomes So, that is what you get if you sum total the two things. So, what does this term actually means? We have already covered that. This is the mass transfer, right, from all other phases. We already knew about this, right, all other phases to the kth phase due to phase change. Is that right? So, this we already did it earlier, right, this entire thing we did earlier, right. So, this is the all the mass transfer that is happening from all other phases coming over to this kth phase, because this equation we are writing it for the kth phase. All other mass transfer means it can be mass transfer from this phase to those phases also, right, it does not mean that it is always a mass coming in. And so therefore, this particular quantity is nothing but summation of j equal to 1 to pi, where j is not equal to k if it is the kth phase, m dot triple prime j k, right, transfer from all other phases to the kth phase. That is why if j equal to 1 to pi, but not j cannot be equal to k, got it. Okay. So, this is the transport equation when you actually do the phase averaging thing. Okay. So, this represents actually the phase average. So, in the next class we will extend this, or the next lecture we will extend this and see in what ways this can be used, okay, for developing the other equations, and let us see that those equations are basically the as I said, the volume averaged multi-fluid models. We will look at the energy, there are lots of the standard equations, okay, and we will also look at that. If we have next, we can also look at what about the homogeneous equations also. Okay. So, this is for each individual phase. So, we have introduced it, and in the next class, in the next lecture we will pick it up and see how we can take it forward. Thank you.